So in table 2.6, we see numerical prefixes for hydrates and binary covalent compounds. And this is going to come in handy again for naming compounds that are hydrates and also binary covalent compounds. That comes from the bonding of two nonmetals. So hydrated ionic compounds. So ionic compounds called hydrates have a specific number of water molecules associated with each formula unit. And I'll give you a couple of examples of that. So the water molecules are shown after a centered dot in the formula and named with a Greek numerical prefix before the word hydrate. So an example would be this compound here. So if I have MgSO4, so if you remember from our previous video, SO4 is sulfate, Mg is magnesium. So this would be magnesium sulfate. But in that compound, it can have water trapped inside the crystal lattice. And for every one formula unit of magnesium sulfate, it can hold 7 water molecules. So I put that centered dot, and then I put 7 as the Greek numerical prefix, and then followed by H2O, which is the hydrate. So hydrate meaning the water. So I would call this magnesium sulfate heptahydrate, because hepta is the prefix meaning 7. So I would call this magnesium sulfate heptahydrate. So that's Epsom salt. Another example would be sodium carbonate decahydrate. So if you remember carbonate, the polyatomic ion carbonate was CO3 2-, and sodium has a charge of +1. So I need to have 2 sodiums. So I'll put Na2 to balance out my carbonate. So there's sodium carbonate. And in sodium carbonate, for each formula unit of sodium carbonate, it can hold 10 water molecules. So I'll put 10 followed by H2O. So this would be sodium carbonate. So I have 10, so it would be deca. So decahydrate. So I'll put that in, decahydrate. So you need to know all of these prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca, because any one of these could come up in the class. So let's take a look at a really fun problem here. So it says here, give the systematic name for each formula or the formula for each name of the following compound. So if I look at the first one, I have Fe. So you might remember that that's iron. And then I have ClO4. So ClO4, that takes on a -1 charge, and that is a perchlorate ion. So that's a polyatomic ion. So I have an iron and I have a perchlorate. Now you might remember that the charge of a perchlorate, so ClO4, is a -1 charge. So since I have 2 of those, so I have 2 negative charges, so you might remember that iron can take on 2 possible positive charges, so iron 2 and iron 3. And in this case, I need to have iron 2. So the systematic name for this compound would be iron 2 perchlorate. There we go. So iron 2 perchlorate. Then it's asking me to produce a formula for sodium sulfite. Now you remember probably that sodium is Na and it takes on a charge of +1. You might remember that sulfate is SO4 2-, but sulfite is SO3 2-, because when I lose an oxygen, I go from 8 to 8. So I have my sulfite, which is a 2- charge. I have my sodium, which is a +1 charge. So I'm going to need 2 sodiums, so sodium with a subscript 2, to balance out the charge of that polyatomic ion sulfite. So there's my sodium sulfite. The last one's kind of a fun one. Based off of the last slide, you can probably tell that this is a hydrate. So this is an octahydrate. So since it's a number 8, so this would be an octahydrate. So the metal is barium, so Ba is barium, and the polyatomic ion is OH, which is hydroxide. And hydroxide has a charge of -1, and barium has a charge of +2. So that means I have 2 hydroxides for my barium. So I call this compound barium hydroxide. And then I have to include my octahydrate. So octahydrate. So those are some good examples of both compounds that you have to name and also a name that you have to be able to produce the formula for the compound.